instability. Now I made this word impending in red because there is a key word here, because impending instability is different from incipient instability.
Excuse me, Sujith. Can we have a very short break to sort out the last people problem? I'm really sorry about that, but I've now got an expert here, and I hope we can go through this. I'll be in touch again shortly.
Yeah, sure.
Please continue.
Okay, so I want to distinguish an impending instability with incipient instability. Normally, these gas turbine combustors, they have some transducer like pressure transducer or accelerometer, and they control the cabin when the amplitude goes up. So they detect when the amplitude goes up. So that is an incipient instability. Impending instability means that your amplitude has not gone up, but at the moment everything is fine, but sometime later things will, amplitude will go up suddenly. So it's not happened, but it's around the corner. That's the meaning of impending, and this is a very interesting distinction. And so when we were young, maybe people like me and Marie and Yanis, when we fell ill, we went to hospital, and then the physician will try to listen to the sound of the heart and maybe feel the pulse. But in modern times, with all the young people go to hospital, they are actually, we have fancy diagnostics to find out what their illness is. But so likewise in combustion technology also, people use a lot of high-level technology. They use lots of laser-based diagnostics, multiple cameras, a lot of things. But I want to go back to the old-fashioned way, and the idea is to simply listen to the combustor and forecast transition instability. For example, if I listen to a combustor, I simply by listening to the combustor, I can tell whether the instability will happen or not, just by my feel as an engineer or technician. So the idea is to listen and forecast the transition to combustion instability by listening to it. So that's a big, my wife accuses that I always only hear her, never listens to her. I think that's a very reasonable accusation, I think. I asked her what is the difference. So she says, when I hear her, that means I'm understanding the meaning of what she's saying. But she says, when I'm listening to her, that means I'm trying to pay attention to the way she says things, the fluctuations in her voice and so on. And of course, she says that I never do that. So it's the same thing with us engineers and technicians. Engineers, we try to hear the combustor by looking at the RMS value of fluctuations and FFT and all that. But we never really, like technicians, how they listen, they can kind of get a feel of the combustor by looking at really listening to the fine fluctuations, the control structure of the sound. So the idea here is to listen and not hear. So the experiments were performed on two combustors. One is a solar stabilized combustor, which is, I won't go to the details of the design because what I'm talking about, for that, the details of the combustors are not important, but basically it's a vacuum phasing step. And on the top combustor, there's a spoiler, which is used to hold the crank. And this design came from American Prof, and we have modified this to remove the swirler and put a block body, so we could have two different flame holding mechanisms, so that we want to make sure that our crankings are holding any kind of combustor. This is the photograph of the combustor, and it's a very nice combustor, but we didn't want to do the experiments in such a nice combustor. This combustor has been closed all that need that. So I want to put an ugly little combustor with no windows and so on, and just put one pressure transducer, just like the physician's stethoscope, and try to measure the sound. So that is the objective here. And so simply listen to the sound, and when you predict impending instability, don't go for anything fancy. So I thought before telling anything about instability, I should first look at what is state compression. Because unless you know what is stability, I thought it was completely meaningless to speak about instability. So we, during table operation, to read the papers, they would say this is actually wrong. Even during stable operation, if you go to a turbulent combustor, you will always hear noise, and this is called combustion noise. This is the terminology that is used by engineers. This term combustion noise is actually a misnomer because it is not noise. Actually, if you do rigorous analysis, which I'm not going to talk about, but if you carefully pay attention, combustion noise is actually deterministic chaos. It's really not noise. So deterministic chaos means there is short-term predictability. That's the meaning of chaos, as opposed to noise where there is no predictability. So a chaotic has a self-similar structure with patterns that fill non-integer dimensions. If you zoom into a signal, you would see something similar, and if you split to the small part of it, you will still see similar things, and you can repeatedly do this. So the top is a unzoomed signal. If I zoom into the first half of the signal, I would still see similar structures, and if I still zoom in, I would continue to see this structure. So I thought combustion noise is self-similar, and I want to investigate this. So self-similarity has been investigated by mathematicians like Madras. So I just wanted to, I like this poem very much. Clouds are not spheres, mountains are not cones, coastlines are not circles, but are smooth, not as lightning, travel in a space. So all the human-made objects are nice, circles, spheres, straight lines, boxes. But nature never does that. Nature has rough edges, whether it's geometry or whether it's signal in nature, whether it's, if you look at our heart rate signal or the ECG signal, they're all rough, they're never sinusoid. Geometry is never circular. So we never see Euclidean geometry in nature. Only you see Euclidean geometry only in human made. So nature does display self-similarity. If you look at a tree, I don't know, as leaves come back, is it spring or I don't know anywhere. But if you look at the tree, it's a nice tree, but you can see that the tree branches and then again branches and again branches and again branches and again. This keeps on branching a lot of time. Likewise, if you look at our air passages in our lungs, they branch 26 times. Our blood does keep branching. So there's kind of fractal geometry in the nature. Now, all this is fine, interesting, but do we care about it? So the question is turbulent flow having a fractal nature? So turbulent are actually self-similar. What is shown here is a plume, except that there's a plume in nature about spinning. And you can see that the first picture is the unzoomed version, second picture is the zoomed version, and if you further zoom it, you will get the third picture. And all of them have similar structures. So the images, or if you take signals, so they look statistically similar under freezing efficacy. So the inertial cascade turbulence formed by hierarchy of eddies. So there is no intrinsic scale as viscous effects are absent, and that's where you see this fractal nature. So this is a very, I thought I'll show this picture, a very interesting picture of a galaxy, and you can see this fractal nature of the galaxy. And this origin is from fluid mechanics. So that is self-similarity. Fractals provide a natural framework. This is the subject introduced by Madras, or made popular to mathematicians. Some more engineers, we don't use this fact of this, although I think we should. What is a fractal dimension? So Madras asked this rhetoric question: how long is the cost of treatment? So the idea was that the answer depends on the ruler with which you measure. The length depends on the ruler with which you measure the length. So if you use a large ruler, you miss any of the small ring. Whereas if you use a smaller ruler, you start seeing more and more wrinkles, and you will see, you will end up getting a longer measure. If you take an even further smaller stick, you will get even longer length. So the idea is that the perimeter drive this with ruler. As the ruler size small, the perimeter becomes larger and larger. So this is for geometry. What happens is the dimension of a time series. So for a fractal, measures of dispersion such as standard deviation would not converge. So what we do to take the time signal, split it into small segments, find the standard deviation, and find the average of time. And we plot this log of standard deviation versus log of time scale, that is a log plot. And first we look at the sine wave. You will not see any scaling. So whatever you do, you will get a slope of 0. Now if you look at white noise, you will get a slope of 0.5 or half, because that is a nature of noise. But if you look at signals from combustors, you will get a stable operation. You will get value between 0.3 to 0.2. So this slope is the Hertz exponent, and its name is given on our French scientist Hertz, and name was given by Madras. So signals can be classified as persistent and impersistent. The persistent means upward trend is continuing to be followed by upward trend, or a downward trend will continue to be followed by a further upward trend, like stock markets are going today. Going down, yesterday also went down, maybe tomorrow also will go down because Corona. On the other hand, if you have an anti-persistent signal, if things go up, they will come. If they come down, they will go up again. Now, white noise is where what happens today has nothing to do with what happens yesterday, and what happens today will not affect what happens tomorrow. So, combustion noise actually has anti-persistent attributes, because if you see for anti-persistence, you should get a Hertz exponent between 0 and 0.5. So, signals, and this imaginable because thermoacoustic signals, they are basically acoustic signals. So, acoustic signals are mean reverting signals, that is, if the thing goes up, if the pressure goes up, even it will come down. Because a compression wave will definitely be followed by expansion wave. If the pressure comes down, eventually it will come back up. It's a mean reverting. So signals with single scaling behavior are called monofractals, and by nature more complex than that. So a monofractal description was found sufficient to describe turbulence for shown within fractal. That means there is a whole lot of scaling. That is the meaning of complexity. So there are different scalings for different amplitudes. Small amplitude fluctuations would scale one way, large amplitude fluctuations would scale in another way. So that is complexity. So once again to recap, so if you look at this form of standard deviation versus time scale, you don't this plot divergence between the value is this structure function is dependent on the time over which you calculate. So this slope is called Hertz exponent. Now we try to define what is called a generalized structure function. This is analogous to the structure function turbulent. So except that when you have the Hertz exponent, we are looking at Q equal to Q. Now we power this thing by Q and measure and then raise it down over Q. Now, if you look at the expression, you can say that Q greater than 0, that is when Q is positive, we are focusing on high amplitudes. Why is it? Because when you have an exponent of a positive number over a large number, the number gets very large. For example, if I 10 power 2 becomes 100, 10 power 3 becomes 1000. So Q greater than 0 will amplify. Now, whereas if you take 10 and power it by minus 1, then it becomes 0.1. If I take 10 power minus 2, it becomes 4.01. So the negative Qs, they actually suppress the amplitudes, but it will focus on the low amplitude. For example, if you take a small number, 0.1, and power it by minus 1, it will become 10. If I take 4.1 and power it by minus 2, it becomes 100. So Q is like a filter. If you use positive Qs, you are amplifying the big signals. If you use negative Qs, you are amplifying small amplitude signals. So this is the generalized structure function physically. So if you plot this generalized structure function, what is the time over which it is calculated? Now you can use it for several value. We use it for lots of Qs, but just to illustrate. So here, we take white, all of them with the same slope of some value. If I take periodic signal, all the Qs will give a same, because there is no scaling, so it will give a slope of 0. Now if I look at the monofractal signal, I would get same slope also, but it's not up. it will correspond with certain factors. Now, if you take combustion noise, you see that each of the line has a different flow. That means each of the spectral functions scales with the time for which it is computed in a different. So if you take these slopes and plot this structure and get the slope in qth order Hertz exponent or the qth order Hertz exponent with q, you get a spectrum. It's not a single value spectrum of q's. It's not common. Now you can actually do some transformation. I won't go to that, but you can actually convert this to a host of fractal dimensions, and this is the singularity trend. So this is like a singularity. This is the how much of the singularity is present in there. So we have a broad spectrum for a complex signal like combustion noise. This is the new way of plotting. In earlier times, they plotted the qth order Hertz versus q, and it would be having non-uniform value. Now, this means that combustion noise is refractive. Now, if you have white noise in contrast, you will get a dot here because it has only one scale, which is 0.5. Now, if you have periodic, because there is no scaling, you will get a dot of 0. Now, if you look at word or body, you will have the broad refractive spectrum. There is a lot of fractal dimension in that. So that signal is very complex. That's the meaning of that. So the spectrum is broad combustion noise, concentrated to a point for white noise periodically. So multifractality disappears on stability. Now the question is, does it disappear abruptly or smooth? So just recap, stable of corresponds to combustion noise, unstable operation is known instability, which is periodic. So how do you go from this chaos to order that fit? And so it's very easy to imagine how you go from stable order to disorder, but can you go from, we are trying to find out how you go from disorder to order. Okay? So I will try to play the sound. I hope the signal is good enough to transmit. So first I'll play the combustion noise. Just let me know if you can listen to it. So this for the split operation, I don't know if you played there. Now I'll play thermoacoustic instability, which may be loud. So this is how tonal signal. Now I'll try to say what happens in between this intermittent signal. So if you see, if you could hear it, not sure if you heard it, that you can see both the characteristics of stable operation as well as the instability. So switching between low amplitude and a periodic and high amplitude tone. So between chaos and order, we have intermittency. And so if you have a turbulent combustor, this is only for turbulent combustors. If you have turbulent combustors, intermittency will precede the onset of thermoacoustic instability. So this is not just thermoacoustic, but if you look at aeroacoustic system or aeroelastic systems, you will see this intermittent burst. So the top is a thermoacoustic signal, and here the aero signal. This also shows burst, and so we go from combustion noise through intermittency to full-blown instability, or chaos through intermittency to full-blown instability. And this is not just in thermoacoustics, but any aeromechanical instability, like aeroacoustic, elastic, with vibration, surge, etc. So we need tools and measures to quantify transition from chaos to periodic oscillations via intermittency. That's the thing here. So if you look at the amplitude, on the left side we have a solid phenomena, on the right side we have a non-body phenomena. If you look at the pressure versus the parameter, control parameter, you see that the first 3-4 points, there is hardly any sound. But if you look at the Hertz exponent, this is really, the first 4 points is plummeted. So you can see that although there was hardly any sound, the surge exponent is headed towards a full-blown instability. Now, on the right side, we have block-produced stabilized combustor. So you see that the amplitudes are very low, and then there is a surge spike. Even in the first fighting point, when there is hardly change in the amplitude, you see that the surge exponent is being really bad, and you can really understand, you can really get an indication that we are going towards stability. Although the graph measures such as RMS value pressure or FFT amplitude would not show any change at this point. So likewise, as we approach impending instability, the Hertz exponent approaches and multifractal spectrum collapses to a point, we have also multifractality. And this happens for any turbulent current, not just these two burners. So when you have to facing this question, are we going this way? Now we know the answer because we can look at the Hertz exponent and it's going to move well ahead of the instability. So with this wide idea of outside thermoacoustic, here is a picture of aeroacoustic signal, and you can see it stays small and then it jumps up, but we see that the Hertz exponent is moving well even before this amplitudes are rising. The same thing we have shown that works in air elastic like flutter, and we have some patent on this. Now I want to talk about how to analyze a dynamical system. So normally theoreticians write the right dynamical system as dx by dt equals f of x. X is all number of state points. So if you're doing simulations with computational mechanics, CFD simulations, we have very large number of data points, and you have values of pressure, velocity, temperature, etc. all these points. So you have we know the entire state vector in numerical simulations, CFD simulations. But when you experiment, you have one microphone, and that's all we have, as opposed to a CFD who has lots and lots of data coming out of the simulation. So what do we do? So we can do something of phase-space reconstruction, where we can take one time series and find something of average mutual information. I will not do it. Just note down these terms and you'll have to look it up. So average mutual information is that tells how much of the information is missing. And we find the time delay at which mutual information is needed. And delay time series like 30. We have P of t, t plus tau, P of t plus 2 tau. Tau is the delay which corresponds to minimum of average mutual information. That means time series are independent. Now we also try to find the number of dimensions that we needed to embed this. Now to find that we embedded it in 1 dimension, 2 dimension, 3 dimension, 4 dimension, and keep on increasing the embedding dimension. At some point, the phase space will not change anymore. So that would be the embedding dimension. And we can then construct what is called recurrence plots. This is a very important tool in nonlinear dynamics. We first have take the phase plot. If we start at some point, and then we epsilon ball of that. Epsilon ball means it's a ball of size epsilon in d-dimensional space. And if the trajectory recurs, so if you put and it comes back here, it has recurred in the ball. Then you put a black dot. Now consider this point. So here the trajectory recur in point. So this is side. So then you put a white dot, and you get patterns. And this is called recurrence plot. So you can either plot it with black and white dots, you can write a matrix with black dots, you can put 1, and for white, you can put 0. So you get patterns, and human beings are very good at detecting patterns. So a limit cycle could appear as diagonal line in a recurrence plot. So if you find the spacing between these lines, that would correspond to the time period t. Quasi-periodic signal will have diagonal which are diagonal, but there will be uneven space and will be broken. Now, if you are intermittent signals, you have black and white pictures. patches means you are stuck inside the ball for some time, and then comes out, it is showing white. So now, how does the transmission look in the reference block? So this is stable operation of the combustion noise. The signal looks grainy. This thermoacoustic instability, and you get diagonal lines. And this is intermittency. So you see this black and white patches. And the reference plots can be used to measure, to get a lot of statistics, and it's very good tool. You can actually measure the proximity instability. So, although the pressure amplitude rise suddenly, you can obtain things like entropy of the signal or how much time the signal is trapped in the slow regimes, that is the black patches, or recurrent rate, which is the density of black points. All of this will indicate the transition ahead of the rise in amplitude. So there are many precursors, and you can remove the false positives, the false negatives, because you have more than one. Now, I don't know how much time I have, so I want to talk complexity. So, our signal during stable operation was very complex. It was multifactorial, it had lots of fractal dimension. And when you went to thermoacoustic instability, we went to a sine wave. That had no complexity. Sine wave is a very Euclidean kind of thing, so there is no complexity. So, onset of thermoacoustic instability corresponds to loss of complexity. So, the signal plus noise paradigm, which engineers do always, not very good for looking at thermoacoustic instability. And then keep a thing. But this doesn't do very well to capture the event instability. Don't track the fluctuation uneven. So the signal plus noise paradigm, I would say, is adequate to describe the onset of impending instability. And the irregular equations hold the. Now, last part of it, I want to say a little bit into complex system theory. So look at onset of thermoacoustic instability. We see stable operation, and then you see intermittent, or the FFT is starting to steepen, and then it's steepening further and becoming very steep. Now, you start with a shallow peak, the FFT, and you go towards a sharp peak. Question is, how shallow is shallow, or how sharp is sharp? This is a question that you want to address. So there's a pattern that is emerging during this transition, and this needs to be identified and analyzed. The concept of discovering pattern discovery. So we want to say the combustion dynamics is complex. Now, is this just a rhetoric like politics per se, or is it really, can I use complex system theory? Complex system theory has been used very successfully to study physiology or in front of agents and so on. So in a reductionist approach, focus on the parts. So if reductionist people are studying elements, they will look at individual parts and if they hope. Now, in complex system approach, we focus on the interaction. We don't go so much into details, but we focus on how the components or the processes interact. So the change of mindset. For example, if you look at flag, the flag of India, but it's actually composed, constructed by people in a stadium holding placards. So here so there are simple rules. Here there are people showing green placards, here there are people showing white placards, here there are people showing saffron or orange placards. So a reductionist approach will never say anything about it, because you can zoom in on well people, but that will miss this flag. The flag is seen only at the whole, not at the deep. So the whole is different from the sum of the parts, and there are certain emergent properties that are there only in the whole. So now, in this approach, we want to look at the patterns of connectivity in thermoacoustic systems. So we can derive something called networks time series. So there is this thing called network time series parity. That is, for every time series you can construct a network, for every network you can construct a time series. Now, what is a complex network? So, a simple concept. We have nodes and so imagine for times and we get all the local peaks, and when you can connect to local peaks, if one can see the other, So this you can see this, you can connect this, we can see this, you can connect, but this cannot see this, so we don't connect. So this algorithm is called visibility algorithm. You can, if the peak is visible, connect that, visible, you don't connect. And so we can use this to learn something about state. So this combustion noise, the single operation. So if you connect the network this, and you will see that they feature they belong to scale network. So there's automatically probability that how many connect there, number of connections. So P of K is a fraction of nodes having K number of connections, and K is the number of connections for each node. So you plot P of K, the scale and plot, it will this straight line behavior. The slope is 2.7. Some networks in the world have the slope between 2 to 3. For example, you construct this airline or network, lots of networks in nature, they all have slope 2 to 3. So our turbulent combustion noise also has a slope there. So we can just such networks are called scale-free network. P of K goes like format. So the top is a constructed signal from the combustor and the bottom constructed combustor. So both are scale-free networks. And what is scale-free? Trend-line network topology. So we look at the transition from stable to unstable operation. So we can see that this transition happens via state of intermittency. So we have this combustion noise, intermittency, full-blown instability transition. So if you look at the network topology, we know that combustion instability is periodic oscillations. So for a periodic oscillation, we can see only the diodes. We get only 2 connections. Whereas for stable operation, we have very fancy network. So we have a kind of network which is scale-free, transitioning to a regular network. So this is the transition from stable network to unstable network. So Maria told me that I should hurry up, so I skipped some of the slides and say that likewise, use the network properties and establish a lot of measures which can also warn us about impending instability. I will not further describe. So I just want to say networks are used now to model for contagion spread. How does coronavirus spread? So this is a completely different complex network theory. You can use that to study the amount as well. So last thing I want to know about synchronization, the heights of curve that quantum blocks hung on the common beam will adjust their rhythms upon coupling. So if you have flames, they also synchronize. On the left, you see flames that are synchronized in phase. On the right, you see flames that are synchronized anti-phase. So we're using synchronization theory. We studied the coupled behavior of acoustic field and heat release fluctuations. So if we look at which is a black signal and clear is a red signal, we can see that during stable operation, heat release are desynchronized. And during that, what happens during intermittency, they are synchronized during the periodic part and desynchronized during the periodic part. And then they go to co-amplitude limit cycle, which we call phase synchronization, where the signals are, the phases of the signals are synchronized. And then we go to a state generalized synchronization, where only the phase, the amplitudes are synchronized. So the first state is combustion phase, which is desynchronized chaos. We go intermittent, which is intermittent phase synchronization. Then we go to a low amplitude limit cycle, which is phase synchronized state in the first state. And then we go to a high amplitude limit cycle. We have generalized synchronization between heat release rate and pressure. And we can quantify this in great detail, but I'm not going to do that. So we go from synchronized state to intermittent synchronization to phase synchronization to generalization. So one thing I want to tell you all, young student, is that you should listen to data. Often we never even look at it, never listen to the data. We listen to data because the human beings have a very good sense of sound. And even people in other subjects, for example, astrophysicists, they record the light from the earth and then play it to us, and then to get a feel of it. So we thermoacoustic people, it's a lot of data. Then 50 and 100% and all that, never bother listening to it. So I suggest that you keep listening. There's a term called sonification of data. Our signal is sound to begin with. So I would say we should really listen to the sound. So I just want to take an interim summary here by saying that combustion dynamics is complex. It's very complex. You saw there were lots of scaling exponents, and you saw that there was a scale network. These are characteristics of complexity. Now, often when I go to conference, I hear a big shot professor saying combustion dynamics is complex, beast, and so on and so forth. But what do? We actually shy away from the complexity. We average out turbulence, write the equations, and convert this beast to another animal which we can tame. And then we linearize the signal, and then it is a smaller animal, and then we say, we are like a house saying, and a linearized land. So I would say, let complex combustion dynamics be complex, and now the complex system is very advanced. It can deal with the full complexity of combustion dynamics, and there's many complexity. There's early warning and many more things. I only spoke about early warning. In the afternoon, I'll speak of some other things. So what I would say is, it's that complex, embrace complex. Let's stop here. Thank you. Have a good life. If you have questions, I'll be happy to answer. Let's stop.